what is important, particularly important in reforestation and in trees generally, is to understand what is a shade-demanding tree and what is a light-demanding tree, because this doesn't seem to have been taken into account in forestry, in modern forestry. This is a photograph taken on my property in Australia shortly after I cleared some land around these two trees. This area under here was covered with a very dense undergrowth, lantana it's called, which goes wild in Australia. And so these two trees, which are these two trees here, grew up with the bottom part of their trunks protected from light. About 4 weeks or 2 weeks or so, somewhere in that sort of period, I noticed that one of the trees was growing some branches on the lower part of its trunk and the other one was not. And I'd been looking at this because I had also been studying this with been involved with Viktor Schauberger's concepts for quite some time. But this tree is a shade-demanding tree because it's put out branches to protect the trunk from sunlight. The other tree is a light-demanding tree. It has a much coarser bark and it didn't put any branches on. Now, why did the tree put branches on? What was the necessity for a shade-demanding tree to add branches to itself? Well, what is very critical for a tree and for the health of the tree is the movement of sap and the tree's internal temperatures. So that when the sun impinges on thin bark, of course there's no insulation or virtually no insulation, and the temperatures within the tree start to rise, and this causes a dislocation in the natural movement of the sap. So in order to protect itself, the tree immediately puts branches on the outside against the sun. So while we tend to think that trees and shrubs put out their branches to catch the light, they do so in fact to protect themselves, their center part of the tree, from light, because otherwise all their metabolism gets upset. Now this is very, very serious when it comes to large-scale reforestation and large-scale planting. Just to show you how this this effect also happens, here this is again a profusion of small branches. This tree was suffered from a forest fire, and so all the way up every branch as far as possible there were little shoots brought out, because in the fire all the outside skin of the tree had been turned black, which absorbed all radiation and all heat. So if the tree was to survive at all, it was absolutely imperative that this blackness should be protected by a color which is natural to the tree and would normally reflect the sunlight. Again, by overexposure to light demanders, when they're overexposed to light, they produce some peculiar characteristics. This is a small beech tree growing at the side of a forest, and normally most of the development of a beech tree is up in the crown, but there are myriads of little branches down below which make the wood very knotty. Again, because of the disturbance in the sap flow, this is another shade-demanding tree, and you can see that the trunk is actually conical, and that is because due to the heating processes within the trunk, all the nutrients are deposited sooner than they should be, which adds to the girth of the trunk. Whereas that same tree in its natural state would have a virtually cylindrical trunk, and all the development would be at the top. This tree here has been exposed to electromagnetic radiation in the form of radar and microwave activity, which has created a distorted form of the tree. You can see how chaotic it looks. According to the German engineer Dr. Wolfgang Volkort, microwave senders, which are these communication senders, act in the same way as microwave ovens, and any living thing exposed to them gets cooked virtually from the inside out, because he noticed that in Germany, when a new tower was put up, and he made a study of it, on all the slopes of the hills and mountains facing the tower, the trees began to die off, and on the opposing face, on the shadow side as it were, they were still okay. And one of the reasons for this is that one of the wavelengths that they use for microwave transmissions is 21 centimeters, which is the natural harmonic wavelength of hydrogen. And so the hydrogen atom within the water molecule becomes excited and disturbed, and perhaps even removed from the water molecule, which then of course upsets the whole of the sap flow and everything else. But it would also upset anybody else who happened to live there. If trees can't move, they're rooted to the ground, human beings and animals can. But I would imagine that because of this, that anyone living under the path of one of these microwave senders would be more susceptible to disease than someone without. That was a slight digression. I would want to continue with the effect of light and understanding it on trees. Here there's another tree with the branches all on one side. And again, from our conventional point of view, we'd said, oh, well, it's got the branches here because that's where the sun is, and it's putting it out to catch the light. There are no branches on the other side because there's no sun. In effect, that is true. But the proper interpretation, or at least Viktor Schauberger's interpretation, is that the tree put branches out in order to protect itself from the sun. No branches would go on the other side because it didn't have to protect itself from the sun, which is exactly the opposite way of looking at things. Viktor Schauberger often said that if you want to know the truth of how something should be done, find out what today's technology is doing and do exactly the opposite, which means really a 180-degree change in our point of view. Here, another tree, this is a tall pine tree. You can see there's a lot of branches all the way up and down the trunk. It must have been left perhaps as a mother tree in order to provide more seed, but when its neighboring trees had been cut down, then it had the necessity to grow all these branches up and down the trunk on the outside in order once more to restore its inner temperature conditions, crucial to it. These again, that's the same one as before. Again, here's another tree. The lower branches have been cut off, and then suddenly you get a profusion of branches growing on it again. Same reasons. And when you compare the girths of naturally grown and artificially grown plantation timber, now this is a fir, a shade-demanding fir, the big one, and as a result of overexposure to light, then all the annual rings have been spaced apart, the wood is spongy, the whole metabolism of the tree has been upset, and so you get huge growth. You get quantity at the expense of quality. There's no quality in this, and most of this wood would be unsuitable for any structural purposes. Whereas these other trees here, also fir, are the same age as far as can be seen, because their annual rings are so close together they're almost indiscernible. So these are the two differences. This is very high quality wood, and this is very low quality wood, and this sort of wood is what is being produced in most of the plantation forests and so-called reforestation projects. Because in all reforestation projects, it should be important, it should be obligatory to plant as many different species as you can instead of a single species. Otherwise you arrive at a monoculture, and once you have a monoculture, you introduce into a natural setting what used to be a cooperative process into a competitive process, because all the trees in the monoculture have to draw their nutrients from the same horizon. They're all the same species of tree, they've got the same root patterns, they take the same amount of moisture, they take the same energy from the sun, they reflect the same light frequencies, and so there's a total wastage of energy at the same time as the tree is also trying to take from its neighbors whatever it needs to survive.